Hello. Okay, so last time we were talking about communicating states. So those are states in a discrete time Markov chain that are accessible from one another. Okay, so you can, starting from I, you can go to J, starting from J, you can go to I. And of course, like this should have like a mathematical definition. So J is reachable from I if there exists an M such that Bij of M is strictly positive, and I is reachable from J if there exists an L such that Bji of L is strictly positive. And let's call this guy alpha and this guy beta. So last time we did this, but I mean, let's redo it. Basically, we can start with Pii of n plus L. Note that n is arbitrary, but M and L are specific. You know, these are basically those guys here. And we can write this using the Chapman-Kolmogorov equations. So it's summation, you go from I to K in n steps, and then from K to I in n plus L steps. And these terms are all non-negative, and so this sum is lower bounded by just one term, which you can obtain, which you can choose whatever you want, but here it is useful to use K equal J, so that this becomes Bij of M, which can be written in terms of the positive alpha, and then you have Bji n plus L. You can apply Chapman-Kolmogorov again, and again the same idea that you can lower bound this summation with one of the terms, and you choose K equal J, and then you will have a beta, and then Bji of M. So the moral of the story is that you have Pii of n plus L is greater than or equal to alpha beta, which is strictly positive, and then Bji of n. The idea is that you have something that is related to going from I to I. It's related to something that is going J to J. Okay, and of course you can start with Bjj and relate it to I. So as we have seen last time, you can have basically those bounds. Each probability is bounding the other, and so. For example, I mean, if you sum basically, if the sum over n of Bjj, if this sum is infinity, well, this summation will be a lower bound on the sum of Pii of n, and if this is infinity, this will be infinity. Okay, and this has a meaning. You know, the sum of the probabilities, if Bjj of n is a natural number, if this thing is equal to infinity, it means that we are talking about a recurrent state. Okay, and so if you take limits, okay, again you have here like lower bound, and you know, for example, if this guy is finite, then it forces this guy to be finite, and so on and so forth. So as we did last time, that basically because of these inequalities, and again, those inequalities, they require the existence of alpha and beta, the positive alpha and beta, which means that we are talking about communicating states. So communicating states, they belong to the same class. Okay, so if I tell you that I is recurrent, then it must be the case that J is recurrent. If I is null-recurrent, J is null-recurrent. If I is transient, then J is transient, and so on. So states that communicate, they share the same class. Moreover, I mean, so basically this was the last time. Actually, we can say more about this. You know, remember that we also did a classification based on the period. You know, basically there are aperiodic states and there are periodic states with a specific period. So again, communicating classes will share the same property. So if one of them is aperiodic, everyone is aperiodic. If one of them has a period of 7, then everyone has a period of 7. So let's make the argument. So again, let's focus on J and I, and these are communicating states. And the period, by definition, will be that you go to a Bjj of n and search for every n for which Bjj of n is strictly positive. So these are the time instants at which it is possible, it is with a positive probability you can start from J and end up in state J. And the GCD of those n's will be dj, again, you know, from the previous lecture. If this number is 1, we say that the state is aperiodic. If this number is greater than 1, then the state is periodic, and the period is equal to whatever number that you get here. di is the period of state I. Okay, and again, it has the same definition, but rather than using BJJ, now we are talking about PIR. Okay, so let's see why communicating states share the same period, or they are aperiodic at the same. It cannot be the case that one of them is aperiodic and the other is periodic. Okay, and if they have the same period, if both are periodic, then they must have the same period. So here is the argument. From above, we have PII of n plus m plus l is greater than or equal to this positive quantity BJJ of n. Okay, and alpha beta is a positive quantity. Now, if you choose BJJ of n, if you search for the time instance at which BJJ of n is strictly positive, at those time instance, it must be the case that BII of n plus m plus l must also be strictly positive. So this equation tells us that BJJ of n being positive logically implies that PII of n plus m plus l must be strictly positive. Okay, so it means the following. I mean, at what time instance, and this is for every n for which this thing is positive, this PII of n plus m plus l will be positive. Okay, and what are the times for which BII is strictly positive? What are those times? By definition, those times for which BII of n is, or BII of the time index is positive, those are all multiples of DI, because DI is basically the GCD of all of them. It's the greatest common divisor. And so all n's here must be a multiple of DI. So for every n that makes BJJ strictly positive, it must be the case that DI divides n plus m plus l, which means that n plus m plus l must be a multiple of DI, or is divisible by DI by definition. Okay. Okay. Now let's do another quick use of the Chapman-Kolmogorov equations. So PII of m plus l is equal to, and then you sum over state k, you go from I to k in L steps, and then from k to I in L steps. Again, sum of non-negative terms, and so this is lower bounded by one of the terms, and then you choose k to be equal to j m bji of l, and those are alpha beta, which are greater than 0. Okay, so PII of m plus l is also positive. So it must be the case that DI divides m plus n. Okay, DI is a divisor. It's the divisor of all time instants for which this probability is strictly positive. Okay, and so PII of m plus l must be strictly positive, and so DI also divides m plus l. And we know from the divisibility rules that if DI divides n plus m plus l and DI divides m plus l, it must be the case that DI divides the difference between them, divides n plus m plus l minus m plus l. And so DI divides n. So DI divides n. Okay, so what is the conclusion here is that n is a multiple of DI. So every n that makes BJJ of n strictly positive must satisfy it. It must be a multiple. It must be a multiple of DI. It must be a multiple. All those n's are divisible by DI. So DI divides every n such that what? Such that B JJ of n is strictly positive. Okay, So di is a divisor. But who is the greatest common divisor? The greatest common divisor, okay, so every n such that bjj of n, the greatest common divisor is dj by definition. This is how actually we define the periods. So di is guaranteed to be a divisor. dj is the greatest common divisor, then di is less than or equal to dj. So based on our argument, it must be the case that di is less than or equal to dj. But again, the argument can be reversed. Okay, so here we started using basically using this inequality. But remember that we can swap the rule of j and I as above, and so basically you can show also, so similarly you can show that dj is less than or equal to di, and hence di is equal to dj. So for communicating states, again, they belong to the same class. Both are aperiodic, or if they are periodic, they will share the exact same period. Okay, so the idea of the proof here again is to take the set of set of time instance, okay, in this set, for which bjj is strictly positive. Now there is instance, there are instances of time at which pii is lower bounded by the product of a positive quantity and bjj of n. So at those time instance for which bjj of n is strictly positive, this guy here at time instance n plus m plus l will be strictly positive. Okay, so basically being strictly positive means what? It means that at those time instance, it is possible with a positive probability to be in state I, given that the chain starts in state I. So what are those time instances? They are multiples by definition. By definition, they are multiples of di. Okay, so they are multiples of di, and so di divides n plus m plus n. Then we can do a small scale application of the Chapman-Kolmogorov equation and show that basically m plus l itself is a multiple of di. At time instant m plus l, it must be the case that bii is strictly positive. It's lower bounded by alpha beta, and this is strictly positive. So di divides also m plus l. So it divides the difference, and the difference is n. So for every time instance for which bjj of n is strictly positive, it must be the case that di is a divisor. So di is less than or equal to dj, which is the greatest common divisor. And then we can repeat the same argument, swapping the rules of j and I, okay, because again, both the states communicate. And as we did above, you can start from I, end with something related to j, but you can start from something related, let me show you, basically from the previous time, you start from I, do something related to j, but you can start from this one and relate it to this one. So you can do this version of the Chapman-Kolmogorov equations and show that the opposite inequality holds, which means that di is equal to dj, and so the conclusion is that states that communicate belong to the same clause. Any questions? Okay, so now let's talk about this theorem, and it tells you that if you have an irreducible discrete time Markov chain, and so what is the meaning of irreducible? So it is a discrete time Markov chain in which every state is accessible or reachable from every other state. So when our Markov chain has this property, that every pair of states communicate. For every I and j, I is reachable from j and j is reachable from I. In that case, we call the chain irreducible. Okay, and so now we are talking about a specific class of discrete time Markov chains that are irreducible in the sense that you can reach any state starting from any other state. So the claim is that for those discrete time Markov chains that are irreducible, there is a stationary or invariant distribution if and only if there exists one state that is positive recurrent. Okay, so now let's basically take a step back and see what is going on here. So we had a previous proof regarding the existence of a stationary distribution. Specifically, we used the Farkas lemma to show that if the discrete time Markov chain is finite, it has a finite state space, then it is guaranteed to have an invariant or stationary distribution. But we cannot say about infinite discrete time Markov chains. Now, this theorem it doesn't care. So basically, this theorem is for both finite and infinite state spaces. So here actually we are making a statement that is applicable to the case in which the number of states is uncountably infinite. So, but here we need condition. We need basically the Markov chain to be irreducible. Every state is reachable from every other state. So the claim is that we have a stationary distribution if we need one state at least to be positive recurrent. And it is not just if, it's an if and only if statement, which means that if there is a state that is positive recurrent, you are guaranteed to get a stationary or invariant distribution. And if I give you a chain and I tell you, and it's an infinite chain, and I tell you that it is irreducible and it does have a stationary distribution, then you know that at least one of the states is positive recurrent. So the state that is positive recurrent, let's call it K. So first we will assume that there is a positive recurrent state, and we will prove that there exists a stationary distribution. And actually we will construct this distribution. Okay, so we will define this quantity psi of Ki. It's the average number of visits to state K starting from I not equal to K before entering again into state I. So you start the Markov chain in K before going again into state K. So you start the chain in state K, okay, and then there is a first passage time in which you enter into state K again for the first time. In the meantime, between the initialization and revisiting K for the first time, you may visit state I. Okay, so psi Ki is the average number of visits of state I starting from K before. So this is, you need a constraint here, before revisiting K again. And so basically average means expectation, and so we need a counter, and the counter will count how many times x of n is how many times state I is visited, but under the constraint that K is not yet revisited. Okay, so we need the recurrence time of state k to be greater than or equal to n. So our event is that xn is equal to I, which means that you visit state I, and at the same time tkk is greater than or equal to n, which means that the recurrence time starting from k and then you enter into k again for the first time should be greater than or equal to n. Okay, because here is how we define ipsi. We need to basically to count the number of visits before revisiting k. So I have here tkk is greater than or equal to n. Now you may say something that if I is not equal to k, why not write this as xn is equal to I and tkk greater than n? It should be true like this, because if you know that xn is equal to I and I is not k, then you know that k is not revisited in n steps. It's revisited in more than n steps. So you can put it like this or like that, and the reason we will put it like this, because we want our ipsi of k and I to also be defined if we choose I to be equal to k. So here it's a technicality so that we have ipsi kk is defined. So if you just use the formula, what is ipsi kk? Replace I by k, so it is this. X of n is equal to k, and tkk is greater than or equal to n. So it means that you revisit k in more than or equal to n steps, and xn is actually equal to k. So what is this event? What is this event? What does it mean? It means that tkk is equal to n. So here we say that it is greater, we say that tkk is greater than or equal to n, but x of n is equal to k. So you enter into k again for the first time after initialization at time instant n. So actually tkk is equal to n. Okay, so this is the probability that tkk is equal to n. Well, what is state k? It is a recurrent state. It's a recurrent state, which means that sooner or later you will revisit k. So this summation is equal to 1 because state k, it is this state in the Markov chain that we are sure is a positive recurrency. Again, as a reminder, we are basically doing the proof in which there exists state k that is positive recurrent, and then we want to use this to show that there is an invariant or stationary distribution. So the state being positive recurrent, actually for this part here, you just need the state to be recurrent. Because it is recurrent, then sooner or later it will be revisited. Now the recurrence time becomes a proper random variable, and basically, sooner or later, basically it takes a finite value almost surely. This is in opposition to basically transient states. For transient states, there is a positive probability that actually the recurrence time is plus infinity, but not the case here. So basically this is equal to 1. Okay, now let's do something else. Let's take this quantity and let's basically sum it over I, where this I is in the state space. So this will be summation I in S, summation n from 1 to infinity, probability that xn is equal to I, tkk is greater than or equal to n, given that we start in this recurrent state. Okay, that's a non-negative quantity. By Tonelli, we can do the order anyway, so we can interchange the order, and we can have a summation like this. So here we are summing xn over all possible states And so basically this is equal to n1 to infinity. So this is the joint of these two events. Xn is equal to I, and tkk is greater than or equal to n. And we are summing over all possible values of I. And so we are basically marginalizing, and we are getting the probability that tkk is greater than or equal to n, given that x0 is equal to k. So this is the sum of the probability of those events that tkk is greater than or equal to n. And we know that for discrete random variables that take non-negative integer values, this is actually the expectation of tkk. This is what is called mu kk, the mean recurrence time of state k. And because state k is a positive recurrent state, this is strictly finite. Okay, so we have state k, it is positive recurrent state, and so we define epsilon ki like this, and this quantity has a meaning. It is the average number of visits to state I starting from state k and before revisiting state k. Now, this quantity, if you put I equals k, it is exactly equal to 1, because we are talking about recurrent state k. And if we sum this quantity over all possible state values, then we get mu kk, the mean recurrence time of state k. And this, because state k is positive recurrent, then its mean recurrence time is finite. Okay, so keep this in mind. Okay, let's see what. So what we will do next is that we will go back to epsilon k and I, and we will play with its definition. Basically, we will take this summation and split the term with n equals 1, and the other terms we will leave them in a separate sum. Okay, and we will see why we do this. Okay, any questions? Okay, so far we have this epsilon ki, which is given by this quantity. Again, average number of visits from k to I before revisiting k. If we put I equals k, epsilon kk is equal to 1, because with probability 1, state k will be revisited sooner or later, and then the sum over all states is basically the mean recurrence time, which is finite. So now let's do this splitting thing. We will separate n equals 1 and then the remaining terms. And now here we have tkk greater than or equal to 1, which happens with probability 1. This term here is just the probability that x1 is equal to I, given that x0 is equal to k. So this term here is the transition probability k to I. So the first term is just the transition probability k to I. Now we have a summation that starts from 2. What we will do is that we will apply the law of total probability regarding the state of the discrete time Markov chain at instant n minus 1. Okay, so what we will do is that we will take n to infinity, and then we do a summation j to s, and j is not equal to k. J is not equal to k because if the revisiting time is greater than or equal to n, then we are sure that at time instant n minus 1, basically the chain is not in state k, because it is revisited at instant n or above. Okay, and so what we will do is that we'll do summation over the states excluding k, because if you put k here, basically the probability will be equal to 0. So have a summation j is not equal to k, and we have x and I. So this is what you insert, that xn minus 1 is equal to j, and then we have that tkk is greater than or equal to n, and then x0 is equal to k. Okay, and then what is the benefit of doing something like this? So now, the first thing, now we are sure that at time instant n minus 1 and time instant n, we are not back yet to state k. So because xn is equal to I, and xn minus 1 is equal to j, which is not equal to k, then I can put this as tkk greater than or equal to n minus 1. Okay, I can write it like this. Then we will apply the chain rule. I will write this as the probability that xn is equal to I. This is very important. So now I will condition on those guys, xn minus 1 is equal to j, tkk is greater than or equal to n minus 1, x0 is equal to k, times the probability that xn minus 1 is equal to j, and tkk is greater than or equal to n minus 1, given x0 is equal to k. Now let's look at this first probability. xn, the time instant is n. We are conditioning on xn minus 1. Okay, and this is equal to j. So we are fixing state n minus 1. At time instant n minus 1, the chain is in state j. What about those events here? One of them is telling us that the very initial state is k, and the other one is telling us that tkk is greater than or equal to n minus 1. What does this event depend on? This event, to know tkk, to know whether it is greater than or equal to n minus, what do you need to know? You need to know, if I give you x of 0 up to x of n minus 1, I can tell you whether a revisit of state k has occurred or not. Okay, I can basically check it by just checking this part. If there is no state k appearing, then basically this event is true. If there is state k appearing, then this event it didn't happen. Okay, and so this is what I said last time. I emphasized the fact that the first passage event is a stopping time, and this is very important because now basically we can apply the Markov property, that here we are conditioning on n minus 1. Everything else depends on n minus 2, xn minus 3 up to x0, but by the Markov property, or the extended Markov property, this is just the probability of xn equals I, given that xn minus 1 is equal to j. Okay, so this is the transition probability, ji. And then you are left with this term here. Okay, and so what we did is that, again, the first term is the probability bki. Now the second term, now we write it in terms of bji, and then there is a summation, and this summation, okay, so basically let's do it in slow motion. So there is a summation n from 2, remember, n from 2 to infinity, xn minus 1 is equal to j, tkk is greater than or equal to n minus 1, and then x0 is equal to k. Now replace n, define m is equal to n minus 1. So m from 1 to infinity, probability of xn is equal to j, tkk is greater than or equal to m, and then x0 is equal to k. And what is this thing? By definition, this is psi of k and j. This is psi k and j, the average number of times state j will be revisited from state k before revisiting k again. And then what we will do is that we will insert here before this probability psi kk, which is equal to 1. And we discover something. So the summation here is summation over all states except state k, and it has the form psi kj bji, but then this outer term is psi kk bki. So basically this term here can be basically merged into this summation, so that we have a sum going over all states including state k, and have psi kj multiplied by psi kj multiplied by bji. Okay, again, because here when j is equal to k, we get psi kk, which is 1, and then bki. Okay, so again, this term here, it can be recombined with this summation, and so we get this very important equation, that psi of ki is equal to summation j on s psi of kj and then bji. Now define psi tilde. So we will take basically those psi's and we will divide by mu kk. Remember what mu kk was? It is actually the sum of the psi's over the states, which is equal to a finite number, again because state k is a positive recurrent state. So I mean, that's the reason we need it to be positive recurrent, because if it's non-recurrent, this mu kk will be infinity and we will divide by infinity. So we don't want this. We want to divide by a finite number, and that's the reason that we need basically a positive recurrent state. Okay, and so now this is basically, those are the normalized psi's, and if you look at this equation, it, you know, initially it may seem like meaningless to you, but actually it has a meaning. It's like there is a row vector and one of its elements is psi tilde of k and I, and here we have a summation, and this summation is what you get if you have a row vector and you basically multiply this row vector by the ith column in the transition probability matrix, right? So here you have a summation over j, and this is I, which is the same index here. So have a row vector multiplied by the ith column. So basically the elements here are equal to the same vector multiplied by the transition probability matrix. This is an eigenequation. So here we proved that there exists a stationary distribution, a distribution that, you know, basically all those guys, they are probabilities. You know, the average number of visits and everything here is non-negative, and basically these vectors sum to 1, again because you did this normalization step which required dividing by mu kk, which is a finite number. So here it's not only that we showed that there exists a stationary distribution, we give actually an example of that distribution. So a distribution can be obtained, a stationary distribution can be obtained by using those psi values. Okay, so now we have a vector, and this vector is a stationary distribution. It is so it is, you know, psi of k if the states are, so if the states are 1, 2, 3, 4, and so on, then we have psi k1 over mu kk, then psi k2 over mu kk, then psi k3 over mu kk, and so on. And this mu kk, don't forget, it is basically the sum of psi k and I in S. So it causes, it basically, it makes you, you know, it helps you to normalize and get a vector with non-negative entries whose sum, the sum of its components is 1. That's a stationary vector. It satisfies the eigenequation pi is equal to pi p. Okay, so so now we prove that basically if there is a positive recurrent state, we can come up with a stationary distribution. And if you really go through the proof again, you will find that we need a positive recurrent state. But actually our theorem is stronger. It tells you that the converse is true. So if I give you an irreducible discrete time Markov chain and I tell you it has a stationary distribution, then you know that there is a positive recurrent state. And then we will also talk about uniqueness. So is this vector here a unique stationary distribution, or there can be others? Okay, so there are still some basically loose ends that we need to tie. Okay, so let's again rethink our you know, what we obtained. So what we obtained is that, you know, you can have a row vector with those psi tilde, and it is equal to the row vector multiplied by b. And so we have this vector multiplied by p, okay? And so you can repeatedly use this trick, right? So you can take this vector and write it as the vector multiplied by b, and then you can take this vector and write it as the vector multiplied by b, and so you can basically get this expression. So this psi tilde vector will be an eigenvector not just for the transition probability matrix, it is for all its powers, which is something that we know, right? So if you have a stationary distribution, if it satisfies the eigenequation of p, right? So if you have pi is equal to pi p, then this pi is equal to pi p, right? And so it is equal to pi p squared, and so you can write down this thing as pi p squared. So this is equal to pi p cubed, and so on and so forth. So for every natural number n, this is actually true. Okay. So what is the issue now? Let's see. I mean, we want like to check whether the vector is just a non-negative vector, or whether it is also composed of strictly positive elements. Okay, so again, we know that it is non-negative because of the definition of psi. It is a sum of probabilities. It is the average number of visits. So it is a quantity that is non-negative. But can we say that it is positive? Okay, so let's see. Psi ki is equal to the sum psi kj and then bji in the matrix p to the power n. Again, because of this argument that I said here. And if you divide both sides by mu kk, then you convert from psi to psi tilde. Okay. Now, psi kk itself is equal to 1. You know, actually, the way that we defined psi is to guarantee that that basically we have psi of k, and k is equal to 1, right? What else? Let's look here. We are talking about an irreducible chain. So an irreducible chain means that actually every pair of states actually communicate. Every pair of states are reachable from one another, right? So if you take I and k, you are sure that there is bik of m that is strictly positive and bki of l that is strictly positive by definition. Now, psi ki is equal to this summation here. Let's use here L. Let's use L. You can use any natural number. You can use any natural number of your choice. I will use L. And this is a summation of non-negative terms. So the summation is lower bounded by one of them, and I will choose to set j equal to k. So psi ki is greater than or equal to, and then you put j equals k. So this will give psi kk and bki of l. Now psi kk is equal to 1 and bki of l is strictly positive, then this quantity is strictly positive. And this is for any generic I. This is for any generic I. So basically all states, I mean, so I can be any state. So in fact, the psi values are strictly positive. They are not just non-negative. The vector that we have constructed is strictly positive. So let's say this again. So we have psi ki is equal to summation j of psi kj bgi, sorry, bgi of n for every natural number n. Now we will basically say that psi of k and I is summation g s psi of kj. We will choose n to be equal to L. L satisfies, it's not any L, it's not any natural number. You choose the natural number that satisfies that bki of L is strictly positive. Are we guaranteed to have such an L? Yes, by definition, because I and K are communicating states. Each one is reachable from the other, and so by definition we should be able to find this L. So this is a summation, and this summation can be lower bounded by psi kk and bki of L. Now this guy is strictly positive, and psi kk is equal to 1, then psi ki is strictly positive. And if you normalize, if you divide psi ki by mu kk, then basically you still have positive numbers. So those guys are positive, strictly positive. And don't forget, now that if a state is if there is a positive recurrent state and it communicates with other states, then remember that the first part of the lecture, that communicating states, they have the same class, they belong to the same class, which means that the overall discrete time Markov chain, once we say that it is irreducible and that there is one state k that is positive recurrent, then actually every state is positive recurrent. And in fact, if k is aperiodic, every other state will be aperiodic. And if k is periodic with a certain period, every other state will be periodic with a certain period. Now, we are also saying that there exists a strictly positive stationary distribution. There exists a strictly positive stationary distribution. Okay? So now let's basically do the converse. Let's say that I give you an irreducible Markov chain, and we are sure for some reason that it has a stationary distribution. Now, what can we say about the states? Okay, so there exists a stationary distribution, and it will satisfy the eigenequation of not just p, but any power of p. Don't forget that the sum of the components of pi will be equal to 1. So initially we would say that even if in the stationary vector, even if some components are 0, it must be that there are positive components, because if every component in pi is 0, then it is not even considered an eigenvector, and the sum of its components will not be 1, right? So we are guaranteed that at least there is a pi v that is greater than 0. Okay, now we are talking not about a general discrete time Markov chain. We are talking about a discrete time Markov chain that is irreducible. So for any other state gamma, there exists an m such that bv gamma of m is greater than 0. So starting in v, after n steps, there is a strictly positive probability that you will be in state gamma. So again, this is not a mystery. This is because the DTMC is irreducible. Okay, so here is what we will do. We will take this equation here with a power that is equal to m. So specifically, by gamma is equal to summation g in s by g, and then bg gamma of m. Now, again, we have been doing this a number of times now in this lecture and the previous one, a summation of non-negative terms, it must be lower bounded by one of them, and let's choose the one of them to be when j is equal to v. V is chosen because V is assumed to be strictly positive. The existence of V is guaranteed. Again, you have a non-negative vector, the sum is equal to 1. It must be the case that at least one component in the vector is strictly positive, and I will say that it is component V. So we will lower bound this one by pi V bv gamma of m. Now this one is strictly positive. Actually, I did the lower bounding using j equals v so that I get here something that is strictly positive. And then we have the probability. And we have chosen m such that this probability is positive. And so this quantity is strictly greater than 0. So every pi is strictly positive. So if we start our argument by saying we have an irreducible chain. Now I am not saying that one state is positive recurrent or anything. I am saying that there exists a stationary distribution. So the first thing that we have shown is that if there is a stationary distribution, if there is a non-negative vector with a sum of 1 that satisfies the eigenequation of p or p to any power with an eigenvalue 1, then basically this vector must be strictly positive. All its components must be strictly positive. Okay. Now, let's basically do this. What we will do is that we have pi v. Okay, so let's actually do it like this. So pi v is summation j in S by j and then bjv. And okay, so again, it's because pi is a stationary or invariant distribution. Okay? And this is true for every n. What we will do now is that we take the limit of both sides as n goes to infinity. Okay, now left-hand side. Well, we don't have an n here. We don't have here something that depends on n. This actually is constant with n, and so the limit of a constant is basically itself. Okay. Now we have here a limit, and we have a summation. Now, if the number of states is finite, then without hesitation you can bring the limit inside, because a limit is a limit operation is linear, and the limit of a sum of a finite sum is a sum of limits. But now again, our ambition is that we are also making statements regarding discrete time Markov chains with a countably infinite number of states. So in that case, I cannot just interchange. I need to use one of those theorems, and here the dominated convergence theorem or one of its versions will work. So here is the summand. So summand is upper bounded by j, because the other term is a probability, and the probabilities are less than or equal to 1. So the summand is upper bounded by j. So we need two things now that are satisfied. Upper bound does not depend on the variable with respect to which you are taking the limit. So upper bound doesn't depend on n. That's cool. And the second thing is that the sum of the upper bounds is actually equal to 1, which is a finite number. So by the dominated convergence theorem, we are actually able to interchange the order of limit and summation. And again, this is needed if the summation is has an infinite number of terms, and so we can indeed bring the limit inside. So we can bring the limit inside like this. Okay, now what is the limit? Well, we studied basically that, it depends on what state you are talking about. Sometimes this limit is 0, and sometimes this limit is, is 1, is positive. So if all the states are transient or null recurrent, so this is a previous result. If all the states are transient or null recurrent, we have a problem, because in that case, those limits will be 0, all of them. For every j, this will be 0. So remember, the idea is that we showed that bjv of z using the generating function, if v is not equal to j, this is fjv of z, and then bvv of z. Okay, and so if every state, remember, so basically the idea is that this quantity here will be this is the sum. Okay, so remember this thing, as z goes to 1, this is, so limit z goes to 1 of fjv of z, this is summation fjv of n is a natural number, and this, now this guy is, it tells you the probability of going from v to v from j sooner or later. And in our case here, this probability should be positive. Why? Should be positive because our Markov chain is irreducible. Okay, so it's irreducible, and so every state should be accessible from any other state. And so basically, if you take the limit as z goes to 1, this guy should be some positive number. Perhaps it is equal to 1, but it is guaranteed to be positive. And so basically, this limit here is related to that limit. And if this is finite, this will be finite, and if this is infinite, this will be infinite. Okay. So the idea now is that we have this specific limit here, and if it happens that every state in our Markov chain is either transient or null recurrent, then the limit, again from a previous argument, will be equal to 0. And then this summation here will be zeros. You sum zeros an infinite number of times, it is still 0. But this is a contradiction because by v for every v is strictly positive. So you can see now the structure of the proof. So we assume that there is a stationary distribution. We said, okay, stationary distribution does not necessarily mean that every component in pi is strictly positive, but at least there is one component that is strictly positive. Otherwise, the sum cannot be equal to 1. So we need, let's say, by v is strictly positive. Now, if by v is strictly positive, and given that every state is reachable from every other state, you can show that pi gamma for every gamma is also strictly positive. Okay, and then you go back to by v or any one of the by's, and you play this game. You write the eigenequation, and then you take the limit of both sides as n goes to infinity. On the left, we have a probability that does not depend on n, so it will remain as is, and it will be a positive quantity. And on the right, we will have a limit and infinite, a limit and the sum, We can bring the limit inside by the linearity of limit if the state space is finite. We can bring the limit inside by the dominated convergence theorem if the state space is infinite. Now, if you put the limit inside, then basically, and if you assume that every state is null recurrent or transient, we will have a contradiction because now the right-hand side will be 0 while the left-hand side is strictly positive. So if we start with the assumption that there exists a stationary distribution, our conclusion is that there must be at least one positive recurrent state so that we can avoid this contradiction. But the discrete time Markov chain is irreducible. Every pair of states communicate, and we know that communicating states belong to the same class. So if we show that there exists one positive recurrent state, it must be the case that every state is actually positive recurrent. And we will show that basically the stationary distribution is 1 over mu jj. Okay, it is 1 over mu. So basically there is a very nice relationship between the stationary or invariant distribution and the mean recurrence times, okay, for Markov chains that are composed of positive recurrent states. Okay, so again, let us basically think about what we are doing. Previously we talked about finite discrete time Markov chains. Invariant distribution is guaranteed to exist. Now we want to make statements about infinite discrete time Markov chains, so there is a cost. Well, I mean, you know, if we just talk about a general thing, it will be very difficult to prove statements. And so what we do is that we allow the possibility of an infinite state space, but at the same time, we talk about irreducible chains. So remember, you know, see our arguments here, if you basically move through them, you will find that this issue, this assumption of irreducibility, the fact that every state is reachable from every other state is crucial in the proof. Now, we have shown that if there is a positive recurrent state, there is a stationary distribution. If there is a stationary distribution, there is a positive recurrent state. And because the chain is irreducible, then all states communicate, and so every state will be positive recurrent. Every state will be aperiodic or periodic with the same period. We constructed, using the psi ki function, we constructed a stationary distribution, and we want now to basically relate the stationary distribution to the reciprocals of the mean recurrence time. Actually, we want to show that these two quantities are the same. Any questions? Okay. So let's have again our chain, and let's initialize the chain by a stationary distribution, which means that, you know, basically at every time instant, the BMF of x of n. So the BMF of x of n now does not depend on n. It is basically the stationary distribution. So now we know that our chain, you know, if there is one positive recurrent state, it will have an invariant distribution. So let's talk about one stationary distribution, and let's investigate the quantity mu jj by j. Okay. So leave by j as is, and write down an expression for mu jj. So mu jj, it is basically the mean recurrence time. And so write down, so here we will use basically the summation probability tjj greater than or equal to n, given that x0 is equal to j. Okay. Now, remember that we initialize the chain using the stationary distribution. So the probability that x0 is equal to j is actually by j. These two things here are the same because we initialize using a stationary distribution. And so this pi j can be written as probability that x0 is equal to j, and then the conditional probability times probability that x0 is equal to j can be written as a joint probability tjj is greater than or equal to n, and x0 is equal to j. Before I continue, in the proof on the previous page, when I applied the dominated convergence theorem, I basically upper bounded the summand. And when I upper bounded the summand, I used the fact that everyone knows that a probability is less than or equal to 1. Okay, so we had basically that, let's say that pi j is equal to summation I in S, pi I, and then pi ij of n, something like this. And then we took the limit, and we want to interchange limit and summation. And then we said, okay, I can take this guy, and it is upper bounded by 1. And so by doing this, we can upper bound the summand by something that, or the magnitude of the summand. Here, the summand is non-negative, so we don't really need to worry about magnitudes. We upper bound it by something that does not depend on n, and this is needed for the dominated convergence theorem. Our upper bound should not depend on the variable with respect to which we take the limit. Okay? So far, and everyone here agrees that this is good. However, in the last homework, homework 11, there are 3 students who basically, I think in problem 3, 2 or 3, they upper bounded a PDF by 1. They upper bounded a PDF by 1, which is a very serious mistake. You cannot do this. Okay, at this stage, you cannot do this. A PDF is a PDF. It is not probability. What is the uniform distribution? Uniform distribution on 0 and 1/2. It is a PDF that is like 1, 2. Okay, which is obviously greater than 2. If you do something like this, I mean, people will, there will be a very harsh conclusion. Basically, I will just assume that, you are just stressed. Okay, but this is a very serious mistake. To be learning advanced probability or random processes and to upper bound the PDF by 1. Okay, you can bound a CDF. A CDF is a different story because a CDF is the probability that x is less than or equal to alpha or something like this. You can upper bound it by 1. You can play this game with a CDF, no worries. But for a PDF, there are examples for PDFs that actually tend to infinity. Okay, so yeah, there are examples, you can search for it. An unbounded PDF, yes, you can find an unbounded PDF that is perfectly a PDF, non-negative function that is integrable to 1. Okay, so very important. Okay, upper bounding, you upper bound the probability by 1, but you never upper bound a PDF by 1. Okay, actually, those who did so, actually they deserve a 0, a 0, or really negative marks. Really negative, something like -200 or something. It's really bad mistake. It's one of those, like, there are many things that can be forgiven, because like they are still advanced, you are still learning them and so on, but not this one. Okay, so we come here, and now we have our stuff written as a joint probability. So split this into two terms, n equals 1, and then from 2 to infinity. If n is equal to 1, tjj is greater than or equal to 1. That's an almost sure event because we are talking about recurrent, recurrent states, actually positive recurrent states. And so, sooner or later, basically, you will come back to state j. So this is actually probability x0 is equal to j, and then we have this summation here. And this event that x of 0 is equal to j and tjj is greater than or equal to n, this event can be written in a more expanded form. This is x0 is equal to j. Since you revisit j after n steps or more, it must be the case that x1 is not j, x2 is not j, x3 is not j, up to xn minus 1, this also should not be equal to j. So this event, that you start in j and then you don't revisit j except at time instant n or more, it means that for time instants from 1 to n minus 1, you are not in j. Okay. Now, this probability here can be written as a difference between two probabilities. Okay, so basically, if you have this probability, this is x1 is not equal to j, x2 is not equal to j, up to xn is not equal to j. By the law of total probability, this probability is equal to two probabilities. In one of them, we have x0 is equal to j, and in the other, x0 is not equal to j. And so what we will do is that rather than having this probability, we will rewrite it as this probability here minus this probability with x0 is not equal to j. Okay, and so we have something like this. So basically, the trick here is that we are hunting for a telescopic sum. But we cannot do the telescopic sum right now. It is not still feasible to do the telescopic sum. Again, here we go from x0 not equal to j to xn minus 1, but this is from x1 to xn minus 1. Okay, so we need to basically change the indices so that we can apply basically the telescopic sum. Okay, so here terms will not cancel. So here's the trick. Let's focus on this one here. It can be written as a summation in which x1, x2 up to xn minus 1, they take all possible values except j. So x1 is not equal to j is equivalent to x1 being any state from the state space except j. And the same for x2 up to xn minus 1. Okay, so all those guys can, basically not equal to j, can be written as summation over the state space excluding j. Then apply the chain rule. So by applying the chain rule, you can write down this: x1 is equal to I1, x2 given x1, x3 given x2, and so on. So now here is basically the trick. Now, probability that x1 is equal to I1 is the same as the probability that x0 is equal to I1. Why is this the case? The random variable at time instant 1 has the exact same distribution as the random variable at instant 0. Why? Because the Markov chain has been initialized using the stationary distribution or a stationary distribution. So basically any x of n, so basically x of n's, let's write it, so x of 0, x of 1, x of 2 are identically distributed because of how we initialize the chain. Okay, so this is nice because it will make this one equal to 0. Now our chain, as I said, that we will basically deal with homogeneous chains, so basically things depend on time differences. So going here from time instant 1 to 2, we can basically have 0 and 1, 2 to 3 can be 1 and 2, and so on. So we can rewrite this thing as summation and here we have x0 up to xn minus 2, and again we can rewrite things in terms of not being equal to j. So what did we do here? Rather than having a summation with x1 to xn minus 1, now we have a summation from x0 to xn minus 2. Okay, so we have this. So x0 is not equal to j, x1 is not equal to j, xn minus 2 is not equal to. So that's our h. Now you look at this thing and you say, so what is the advantage? Why it's basically for telescoping. So let's put n equals 2. If n, what is the term corresponding to n equals 2? Okay, and you put n equals 2 here. Okay, so this will be n equals 2. Now what about n equals 3? So in this one, so if n is equal to 3, this will be x1, and then the second one, n is equal to 3, so we will go all the way to x2. And here is the telescoping. These two guys appear with one with a minus sign and the other with a positive sign. Okay, so telescoping now has been achieved, and basically what you have is the following. I mean, what is a telescopic sum? You know, basically it has two terms. So the first term, the very first term, and the very first term combined with x of 0 equal to j will give you 1. When basically this is combined with that, you will get 1. But then when you do telescoping, basically there will be minus the very last term, and you take the limit as k goes to infinity, right? So again, like you can do things in slow motion by putting a finite upper limit here and then taking the limit. The idea is that there will be again two terms that combine to 1, and then there will be this term here. Okay, let's think about this term. This term is this: the probability that x0 is not j, x1 is not j, x2 is not j, up to xk minus 1 is not j, and actually we are taking the limit as k goes to infinity. Now, what is this limit? What is this limit? It must be 0. Why it must be 0? Because this is the event that j is never ever visited, right? So the probability, you know, if you basically put a k here equal a trillion or a trillion to the power trillion to the power trillion, you basically have at all those time instants j is not visited. But this does not make sense because we are talking about an irreducible discrete time Markov chain with positive recurrent states. So every state will be visited sooner or later, regardless of what we start in. Otherwise, the state is not recurrent. So recurrent means that it will always keep appearing. Okay, and so basically, you know, if j is never visited, again, it's either not positive recurrent, or it's basically it is not accessible from every other state. But this does not make sense because we assumed that our chain is irreducible and every state can be reached from any other state. Okay, and so this right hand side is 1, and because the right hand side is 1, it must be the case that this product is equal to 1. Mu jj by j, you know, so if you start with a stationary distribution, it must be the case that by j is equal to 1 over mu jj. But mu jj is like a fixed number for every state j. So there is a unique invariant distribution. So for those irreducible discrete time Markov chains with at least one positive recurrent state. Actually, now we know a number of conclusions. Every state will be positive recurrent. There exists a stationary distribution. In fact, it is unique. And basically, the stationary distribution now, we know like sort of a formula. Basically, it is equal to the reciprocals of the mean recurrence times. And also those can be expressed in terms of the ipsi probabilities I talked about earlier. Any questions? Okay. So now, let's focus on irreducible ergodic Markov chains. So remember, ergodic is not just positive recurrent. Ergodic means positive recurrent and also aperiodic, because again you can have a chain. Of positive recurrent states that are periodic with, let's say, period 2 or something like this. So now for ergodic Markov chains, so the states are also aperiodic. In those chains, because the chains are irreducible, you can show, and we have seen something like this before, that Fij is equal to 1 for every I and j. So there was basically a limit statement that we studied earlier, which is that the limit as n goes to infinity of Bij of n is equal to Fij over mu jj. Now, in irreducible chains in which every pair of states communicate, Fij will be equal to 1. And if Fij is equal to 1, then this limit here becomes very nice. Again, let's see the limit. The limit is Fij, which depends on I and j, generally speaking, and mu jj. Now, for irreducible ergodic Markov chains, so basically the states are positive recurrent and also they are aperiodic, it must be the case that this guy is equal to 1. So the dependence on I disappears. So basically, if you study p to the power n, if you study p to the power n, okay, so Pij of n is basically an element in this matrix. Okay, so element ij in this matrix, Bij of n, right? Now we are saying that as n gets larger and larger, this will converge to a number that is the reciprocal of the mean recurrence time, which is by j now. We know that this is by j. And this is true regardless of I. This is true regardless of I. So for those Markov chains that are irreducible and ergodic, if you see the transition probability matrix, as you raise it to a higher and higher power, something nice will happen. Each row, okay, or sorry, each column, regardless of I. So regardless of I, it means that fixing j, so fixing j, so here it's the jth column, regardless of I, every element on the jth column will converge to 1 over mu jj. Okay, so this is again a very important property for those Markov chains. But you need actually to know that they are ergodic. Every state, you need to check that every state is indeed aperiodic positive recurrent, and that every state is reachable from any other state. If that is true, then again the transition probability matrix raised to higher and higher powers will have this nice property that each column will go, each element in column J will converge, will get closer and closer and closer to 1 over mu jj.